Today's lesson 18 in chapter Keys and Couplings, Flange coupling. In previous class, we have completed muff coupling is a rigid type used for low power transmission and power is transmitted through muff. In split muff coupling, power is transmitted due to friction between muff and shaft. And for high power transmission, flange coupling is preferable. Objectives of this lesson. On completion of this lesson, you would be able to design of a flange coupling for a given torque or power. Draw the diagram of flange coupling with the computed dimensions, that is proportional dimensions. Now the flange coupling. Flange coupling is widely used for heavy power transmission. And this power is transmitted at low speeds. Consists of here this flange coupling consists of two hubs which are keyed to two shafts. The hub extended into flanges whose faces are broad and held together by a series of bolts arranged concentrically about the axis so that their axes are parallel to shaft axis. To ensure correct alignment, one of the hubs has a circular projection which fits corresponding depression in other hub. Here you can see this, the sketch of unprotected type flange coupling. Unprotected type flange coupling. Here, these are the two shafts which are to be joined, and this is one hub, and this is one hub, and this is another hub, which is generally made out of cast iron, and the shafts generally made out of low carbon steel commercially. And these hubs are extended towards the flanges, and these are the flanges, and these two are brought together and held in position by means of bolt and nuts. And in order to ensure the perfect alignment of the shafts which are in collinear axis, there is one recess in this hub. This is, so from here to here it is the recess, circular recess, and there is a corresponding projection in the left hub. That is, this is the projection, and this is projection is perfectly fitting into this recess of this right side hub. Thereby, the axis will be on the same line. That will help you in getting perfect alignment. And these hubs are fixed to the shafts by means of keys, separate keys. Here one key, and this is another key. These keys may be sunk keys, which are made out of generally of the mild steel, or whatever the shaft material, the same may be used sometimes. And this hub as well as the flanges are made out of cast iron generally, and these bolts and nuts are standard components which may be of mild steel or generally. So this is all about the construction details, that means of for this unprotected type flange coupling. Unprotected type Flange coupling. So this is the key, and here is also a key, and this is the hub, and this is the shaft, and this is the flange. So this is all about the construction details of the flange coupling. The bolts transmit torque from one flange to the another flange and then to the shaft. That means if you see the power, let it be the this shaft is driving shaft and this may be the driven shaft. The power will be transmitted from this driving shaft to the key and then to the hub and then goes to the flanges and then goes to the bolts. Through these bolts goes to the another flange to the hub and then key to the driven shaft. This is the torque or the power flow. Shaft, key, hub, flange, bolt and nuts, and then flange, hub, and then key and shaft. So this is the sequence of this power transmission flow or torque transmission flow. The bolts transfer torque from one flange to the other flange and then to the shaft. Now the design of this flange coupling. Design of this flange coupling. Generally, same as in the previous case, in case of muff coupling, the design of muff coupling. Here also in the same way, the flange coupling is designed with empirical relations first of all, and these values are checked for the given loaded conditions. And the proportions for CI flange, here you can see outside diameter of the hub D is equal to 2D, where small d is the diameter of the shaft or inside diameter of the hub, and this is the outside diameter of the hub. And L is the length of the capital L is the length of the hub, which is nothing but 1.5D, and pitch circle diameter of the bolt. That means through the circle there is a pitch circle, that is dP is equal to 3D. Thickness of the flanges TF is equal to 0.5D. This is for unprotected type of flange coupling. And outside diameter of the flanges DO is equal to 4D. This is DO is the outside diameter of the flange, and where D is the diameter of the shaft or inner diameter of the hub. So these are the proportions, standard proportions as per the standards. So outside diameter of the hub D is equal to 2D, length of the hub is equal to 1.5D, and the pitch circle diameter of the bolts dP is equal to 3D, and thickness of the flanges TF is equal to 0.5D for unprotected type flange coupling, and the outside diameter of the flanges is equal to DO is equal to 4D, where small d is nothing but the diameter of the shaft or inner diameter of the hub. These are the standard proportions. Based on these standard proportions, we have to calculate the dimensions of the flange coupling, various parts of flange coupling, and then we have to check for corresponding permissible stresses under the given load conditions. So, let us see, considering a flange coupling transmit a torque of T, D is equal to small d is equal to diameter of the shaft in millimeters, and capital D is equal to outside diameter of the hub, which is nothing but as previously told, that is 2D in millimeters. dP is equal to diameter of bolt circle or pitch circle diameter, which is nothing but the 3D, and dy is equal to outer diameter of flange, which is nothing but the 4 small d, and Fs is equal to allowable shear stress for shafts, key, and bolts. That means that generally the shaft as well as the key and bolts are made out of the same material. Thereby, the shear stresses and the crushing stresses may be same for these 3 elements. So Fc is equal to allowable crushing stress for key and bolts. The Fs1, this is nothing but the allowable shear stress for hub and flange material. That means generally the hub and flange materials are cast iron. That's why this is different. And D1 is equal to nominal diameter of the bolts, and the small n is equal to number of bolts, and Tf is equal to thickness of the flanges, which is as per the previous discussion 0.5 small d, that is for unprotected flange coupling. These are the notations for flange coupling. First of all, we have to calculate the diameter of the shaft by using the power and speed formula. By using power formula is equal to P, capital P is equal to 2 pi nt by 60, and you are going to get T value, that means torque value. By using torque or twisting moment, we have to calculate the shaft dimensions. That means shaft diameter by using torque formula, that is T is equal to pi by 16 Fs dq. With this formula, you are going to get your diameter of the shafts. After getting diameter of the shafts, simply you have to calculate the proportion dimensions of each part of the flange coupling, and you have to check for various stresses induced in all the parts. So let us see, in such case, after finding the diameter of the shaft, let us design a hub. Let us design the hub of a flange coupling. Consider this hub as a hollow shaft. As it is hollow shaft, simply shear stress induced in the hollow shaft, that is hub, Fs1 is equal to 16 capital D into T, where is the torque, by pi d power to the 4 minus small d power to the 4. With this will be the induced shear stress in the hub, which should be less than its permissible value. Suppose if it is not within the permissible value, then once again you have to calculate the dimensions, and once again you have to check for the induced stress, which should be less than permissible value. Check the value of Fs with the permissible value. Design of flanges. Design of flanges. The flange at the junction of the hub is under shear. The flange under the junction means between the hub as well as the junction. It may be a possibility of shearing while transmitting torque. That's why the thickness of flange into circumferential length at the junction of flange as well as hub is nothing but the shearing area. That is pi capital D into thickness of the flange is the shearing area for the flange. If you take, so torque is equal to shear area into shear stress into radius of the hub. So this will be the circumferential length at the junction of hub as well as the flange, and this will be the thickness of the flange, and Fs will be the shear stress induced in the cast iron, and radius of the hub d by 2. With this formula, you are going to get your you have to check for induced stress, because all these are calculated based on the proportions only. So check for Fs1 with value given in problem, that is permissible value. If it is less than the permissible value, then only the design will be safe. Next is design of key. Design of key. It is also similar to the previous muff coupling. Here also in the keys, we have to calculate the standard proportions, dimensions of by using standard proportions, that is W, small w, or width of the key is equal to breadth of the key is equal to d by 4, whereas the thickness of the key is equal to d by 6 or 2 by 3rd of w, and the length may be equal to the length of the hub, that is length of the hub is equal to 1.5d, which is also equal to the length of the key. Then after calculating the width of the key and thickness of the key and length of the key, verify, that means check for induced stresses in crushing as well as shearing of the key, which should be less than their permissible values. As per the proportions may be mentioned as width of the key is equal to d. This should be small d but not capital D, and this should be small d, which should not be the capital D. Thickness of the key, and we have to check for Fs is equal to 2t by WL small d, and Fc is equal to 4t by TL into small d. We have to check for shear stress and crushing stress, which should be less than their permissible value. The length of key may be equal to the length of the hub, as I told you. So after checking the shearing and crushing of the key, if it should be less than their permissible values, then only the design is safe. Otherwise, we have to modify the dimensions of the keys. And last one is design of bolts. Design of bolts. Let n be the number of bolts used, which depends on the diameter of the bolts. And after getting n value, that is 4, 6, and 8, based on the diameter of the shafts. So after getting the n value, you have to check for shearing stress, that is T is equal to pi by d1, where d1 is equal to nominal diameter of the bolts, pi d1 by 4 by d1 square by 4 into n into Fs, shear stress in the bolt into pitch circle diameter by 2, and check for the shear stress with permissible value. And also considering the bolts in crushing, so crushing area will be d1 into Tf, and n will be the number of bolts, and Fc will be the crushing stress, and dp will be the radius at the pitch circle diameter. So with this, you have to check for crushing stress. It should be less than the permissible value, and the number of bolts may be chosen as 3 for shafts up to 40 mm diameter, and 4 for shafts up to 100 mm shaft diameter, and 6 for shafts up to 180 diameter. So with this, We concluded the design of flange coupling. Once again, let us see the design of flange coupling. First of all, you have to calculate the shaft diameter by using power and torque equations. After getting the shaft diameter, you have to assume the hub as the hollow shaft. You have to get the proportion dimensions of the hub and check for the shearing stress induced in the hub. And next is flange. Here also it is made out of cast iron. That's why the shearing stress should be the same as the upper visible value may be same as the hub value, whereas it may fail in two ways. Number one is at the shearing at the junction of the hub as well as the flange, and also it may fail due to crushing also at the bolts, right? And we have to check for this. Next is keys, same as the previous case. Calculate the proportional dimensions and check for crushing and shearing stresses. And then finally the bolts. And for bolts are also you have to get number of bolts and pitch circle diameter as per the proportions given. And number of bolts are same as in the previous you, n is equal to 3 and 4 and 6, which are based on the shaft diameter, and check for crushing and shearing stresses, and this will conclude the design of bolts. And let us see one problem based on this design of flange coupling. Here you can see a 60 diameter shaft. The diameter of the shaft itself they have given for us is transmitting 150 kilowatts power at 300 revolutions per minute speed, and a flange coupling has 6 bolts. Number of bolts n is equal to 6 bolts, and each 18 in diameter. Bolt diameter also given d1. N is equal to d6 and d1 is equal to 18 Find the required diameter of the bolt circle. dp you have to calculate. Its circle diameter you have to calculate. If the allowable shear stress in bolt material is 27.7 Newton per millimeter square. Anyway, this will be easy for us to solve this problem. And direct formula torque is equal to 5/4 d1 square into fs into n into dp by 2, and torque you can calculate by using either the shaft power formula. 2 p is equal to 2 pi nd by 60. After getting torque, simply substitute all the values in torque and then get your bolt circle diameter or pitch circle diameter. Solution, let us see. The given data is power is equal to 150 kilowatts, that is 150 into 10 to the power of 3 watts, and speed n in terms of rpm is 300, and the shear stress for bolt material may be fs, that is 27.5 Newton per millimeter square, and the torque transmitted is equal to 60 p by 2 pi n, and that is 60 into 150 into 10 to the power of 3 by 2 pi into 300, that you will get 4774.65 Newton meters. So that may be converted into Newton millimeters, that is 47,74,650 Newton millimeters. Now let us have the considering shear strength for bolts. T is equal to Fs into pi by 4 d1 power d1 square into n into dp by 2. Here you are having Fs and you are having torque and you are having bolt diameter. N is also have 6, and only unknown is DP. Only unknown is pitch circle diameter or bolt circle diameter. So DP is where DP is bolt circle diameter or pitch circle diameter, and after substitution only the leftover is DP. So the bolt circle diameter or pitch circle diameter is DP is equal to 227.5 millimeters. 227.5 millimeters. So this is all about the discussion that we have made for design of flange coupling, and these flange couplings are applicable in many areas. And in villages we can see these flange couplings by joining an electric motor to the water pump. That is a quite common used in several areas. And here let us see the summary of this lesson, today's lesson. Flange coupling is of rigid type. This is the rigid flange coupling. Why? Because the axis of both the shafts which are to be joined are in the same line and also aligned, and used for high power transmission. Whereas the previous mode coupling may be low power transmission, and also split mode coupling also used for low power transmission. Whereas this is for high power transmission at low speeds, right? And power transmission from one shaft to other shaft takes place through flanges and bolts. That means key, hub, flange, bolts. We are going to take the power transmission in this flange coupling. Protected flange coupling has a rotating bolts and nuts are covered by flanges to avoid the danger to workmen who might be near the coupling. This let us have in the next lesson about the protected flange coupling. And design of flange coupling includes hub design, flange design, key design, and bolts design. The design of flange coupling mainly includes hub, flanges, key, and bolts design. So this is all about, once again, let us see the construction as well. As we have completed so far construction of the flange coupling, also working of the flange coupling, notations, standard proportions, and design procedure, and then we completed one problem. Okay, so with this lesson, let us have a small quiz about this flange coupling. To maintain alignment of shafts for a flange coupling, to maintain alignment of shafts for a flange coupling, keys are mounted at right angles, bolts and nuts are tightened perfectly, projection and recess are made on the flanges, projection and recess are made on the hubs, which is the right answer. To maintain perfect alignment of shafts for a flange coupling. Number one answer is keys are mounted at right angles. Number two is bolts and nuts are tightened perfectly. And C is projection and recesses are made on the flanges. And D is projection and recesses are made on the hubs, which is the right answer. As per previous discussion in this lesson, simply we can say D should be the answer, because as per our thoughts, it should be it is the left side hub will have projection, whereas the right side hub will have corresponding recess, and they will certainly fix one in another Thereby, the axis may be perfectly aligned. So that's why it must be, the answer must be D, right? So B should be the answer, right? So projection and recess are made on the hubs is the right answer. And design of flange coupling includes hub key only, flanges bolts only, hub, flanges, keys and bolts, none of the above. Design of flange coupling includes first A is hub and key only, flanges and B includes flanges and bolts only, C hub, flanges and key and bolts, and D is none of the above. And as per our discussion, answer should be C because it consists of shafts, hub, flanges, keys, and bolts. So they include the design of hub, flanges, key, and bolts. Right? That will be the answer. So right. So with this we conclude our lesson. Design of flange coupling, corresponding construction details, working principle, corresponding notations, standard proportions, and design procedure, and one formula. So with this, we conclude our lesson, right? Thank you.